Hi, welcome to MEN 221. Today we are going to talk about how to calculate the internal forces in a truss. Now, before we go there, we just want to make sure that you understand what a truss means. A truss is an object in which every bar is a 2-force bar. So isn't that nice? Makes your life very easy. It's one of the most efficient ways for transmitting loads. And it's widely used. And it's one of the most stable structures that you can build. It's the stiffest thing that you can build with minimum material. So it's a very popular thing to do. Analysis of a truss requires no new skills than what you have done up to now, except that you need to have a clean strategy for doing that, and there's a systematic process for doing that. And that's what we're going to talk about. So let's start. So the idea for a truss is to focus only on the joints. So in this particular case, I want you to focus only on A, B, C. This is the truss. This is the triangular part which is pin jointed at A, and there's another pin joint at C, and there's a pin and roller at B. The nice thing about it is because all these three things are 2-force members, we can actually get rid of them. That's the whole idea. So what we are going to do is we are going to do a 3-step process. The first step is going to be that we are going to find the external reaction forces, RAY, RAX, RBY, those three things. We can forget about the bars because they will automatically always be in equilibrium. We don't care about them. And draw the free body diagram. After we have finished these external forces, we will draw the free body diagram of each of the ball joints or the pin joints as the case may be, and we solve them one by one. That's it. This is called a frontal solution technique, or in a loose way it's called link hopping. We first solve everything we can at point A, then we move to point B or point C, and then we solve everything we can there. So there's some strategy for figuring out which link to go to next, having solved one of these things. Okay, so this kind of a structure where everything is made up of a bunch of triangles is called a simple truss, and we can solve it in a pretty straightforward way. Okay, there are the forces at each joint. Can you see? They're all along the bars because they're all 2-force members. So we have 1, 2, 3, 4, 5, 6 unknowns. These two things are not new unknowns because they are equal in magnitude and opposite direction. So that's easy to do. Okay, so there are 6 unknowns. If you can do it the smart way or the stupid way. What I mean by stupid way is what the computer does, which is solve it as 6 simultaneous equations for 6 unknowns. You can do that. Or you can be clever and solve it 2 unknowns at a time. We are going to do that. I will show you how to do it. Okay. Okay. Very good. This is pretty easy to do. So there. The reason why these things are all in equilibrium is that they're getting either pulled or squeezed. That's the only things. So compression means things getting squeezed. Tension means things getting pulled up. Okay, so you have to figure out whether things are getting squeezed or pulled up. The way we are going to do that is by looking at the signs of these things. If the sign of this value is positive, then it's getting pulled and so on. So I'll show you in a second. Okay, so here is our truss. So what we do is we look at the whole free body diagram. We are going to isolate the body, draw its free body, calculate the forces and moments like what we would do for any other object. Use the equilibrium equations, summation of forces x equal to 0, summation of forces y equal to 0, summation of moments equal to 0, and solve it. Once we have finished the outside one, then we go to the inside and pick a joint and draw its free body diagram. List the magnitude and direction of the forces acting at each joint. Use the equilibrium equations. Now notice there is no moment, because the joints are actually, all the forces are acting through a single point. So our life is easier. Okay. So moments show up only for this. Notice it says forces and moments, whereas here it says only forces. So learn how this goes. Okay. So let's start. Here is the problem. I have a triangular truss loaded by 2 forces. One downwards 12K and another sideways 10K. We're going to solve it in a systematic way. First thing is to find the reaction forces. So I'm going to isolate the body. And I'm going to draw it. There you go. Notice I don't care about any of the internal forces. I only care about the external forces. There is my axis, x and y, and I have drawn AX and AY and BY. So this is a pin joint, so it has AX and AY. This is a pin roller, so there's only BY. And at C there are two external forces, 12 and 10. The forces in the bars don't show up because they are all inside the FPD. Okay, I don't care about the signs of this, we will worry about that later. Now we know how to solve this. We can set up the equations and I can show you the force table. There you go. I have drawn A, Fx, Fy, Xy, M equal to X Fy minus Y Fx. By now you should know how this thing works. It's a pretty straightforward deal. In this case, there are set of forces at A, B and C. I've drawn all the forces, their locations and everything, and off we go. I can solve it. Summation of all the forces in the x direction gives me 0, means Ax plus 10 equal to 0. Summation of all the forces in the y direction gives me Ay plus By minus 12 equal to 0. And then summation of moments around this point gives me By times 7, 12 times 7, sorry, By times 12 times 4 and then 10 times 3. So you will see all those numbers, 12 times 3, that's right, 3 times 10. Okay, so solve it and we know what we will get, right? We will get all of them. Ax is minus 10. That means that my direction in which I had picked Ax was wrong. Ax was going to point the other way. You don't have to switch it if you keep the same value. Okay, what I'm going to do is I'm going to switch it and draw. Okay, so now that we have finished the outside, now we're going to look at the inside. We're going to find the internal forces. So here is my truss. Here are the reaction forces that I calculated. Notice because it was minus 10 I switched the arrow. You don't have to do it, but I've done it here anyway. Because it was minus 0.857 K, I have switched the arrow. You don't have to do it. Here it was 11.14 K, I've put it. These are the external forces. Now let's look at the internal forces. Now remember, I am drawing, this is actually 3 free body diagrams, one for each pin. Okay, FAC, FAB. Notice that when I go from joint to joint, I'll flip the arrow but not the value. Remember this, right? I'm going to flip the arrow but not the value. So when I go from here to there, I have flipped the arrow. You can see that the arrows are pointing opposite, but the values are the same, FAC, FAC. So if I get minus 10 here, I'm just going to substitute minus 10 there. I'm not going to be clever. And the arrows are all drawn in a way that points outwards. Very good. Now let's start. I'm going to draw the free body diagram for point A. There's pin A. There are the external forces. There are the internal forces. The internal forces are drawn as if they are pulling at the link. So that means if I get a positive number, it is pulling and so it's tension. If I get a negative number, it's pushing and so it's compression. Got it? Okay, very good. So then I'm going to mark the angle. That angle theta is given by looking at this triangle. 4 by 3, tan theta is 3 over 4, so I get theta is 36.86. Now for each force here, I'm going to write its magnitude and its angle. So FAC has a magnitude FAC whose value can be positive or negative. So don't think it is always going to be positive. It could be either way. Okay, and the angle that it makes with the positive x-axis is 36.87 degrees. How do I calculate this angle? Go to the base, see how much the angle is. FAB similarly is 0 degrees because it's along x-axis. The 10K is at 180 degrees from the positive x-axis. The 0.857K is actually minus 90 degrees, not plus 90. It should be minus 90. There, that should be a minus 90. Okay, and then off we go. We set up the equations and we solve them. So the x component will have all cosines. I don't even have to worry about whether they are plus or minus because everything has been taken care of. And the y components are all negative. Off we go. We solve it and I'll get FAC and FAB. There's nothing to it, right? So I want you to understand. We are done with this joint. Now go to the next joint. I have two choices. I can go either to joint C or joint B. I'm going to pick joint B. You can go and do joint C if you like. It's not a problem in this particular problem. Okay. So let's go to joint B. Now new x and y axis at joint B. There's my joint B. There are my two forces. FAB was 11.14 K. Where did I get that? From my previous There, FAB was 11.143. That's what I've used there. Notice I've flipped the arrow but not the value. BY is 11.14K, and then I have FBC is along that. Notice I have only one unknown in this equation, so I really need to set up only one equation. But we are going to do it in a completely systematic way. This angle, notice, is more than 90 degrees from the positive x-axis, so make sure theta is 135 degrees, so be careful about that, okay? Then FAB is 180 degrees and BY is 90 degrees. Why is that? Remember, the base of it, this point, makes 90 degrees, so you have to draw the arrow here and calculate this angle. That's 90 degrees, not the tip angle. The base angle is what we are interested in. So all of them are the base angles, not the tip angle, okay? So off we go and we solve this. So I'm going to write summation of all the forces in the x direction, summation of all the forces in the y direction. If your answer is correct, any redundant equation will be automatically satisfied. If your answer is wrong, the redundant equation will not work. There. So we now got all the values. Now notice that this value I got was positive and these two values I got were negative. Negative numbers means this, the bar is getting squeezed. Positive numbers means that the bars are getting pulled. So this will be called 11.14K tension because it's a positive number. This will be called 1.42K compression because I got a negative number for it. You got it? So that's how it goes. Okay, now let's look at another problem. This is a little bit more complicated, more joints, and I will tell you a little bit about the joint strategy. So again, let's start. We first find the external reaction forces. I'm going to go through this kind of fast. There is the external, that's the free body diagram for the whole body. Notice none of the inside bars matters. The only things that are shown are the external forces on this. You know how to solve this, right? So here is the force and moment table for this one. Right? You can look at it and figure out how this is done. Then summation of all the forces in the x equal to 0 gives me ax equal to 0. Summation of all the forces in the y, summation of moments. We know how this drill goes. And I get ax, by, ay. So the external stuff is over. Now we go to the internal stuff. There's my entire, all my joints, the bars have been removed. Those are all the external forces on it that we calculated. Those are all the internal forces. You can see there are lots of them. 1, 2, 3, no, this is not third, that's the same. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can see there are 12 forces, which means I'll get 12 equations for 12 unknowns. So if you start writing all of them all at once, you will run into lots of algebra, but you can do 2 at a time. So how do we do that? Draw a small circle as usual. For joint A, there's the 10K external force at joint A. This was the reaction force that we calculated. Those are the 2 bar forces at joint A. The forces point away from the link. The angle is 8 by 8, that is 45 degrees. So here is my force table. FAB 0, FAE at 45 degrees, 10K at 90 degrees. Can you see that? So please remember, 10K is not this angle, which is minus 90. It is the base angle, that one. You should always go from the base, not from the tip. Don't go here, go here. Don't go here, go here to calculate the angles. Okay, so that's 10K. And then here's the x component, y component. Everything is straightforward and smooth, and we are pretty much set. Okay, off we go to the next joint. Notice I have drawn some triangles. Idea is don't go from joint A to joint C. You have to solve a triangle at a time. Can you see the dotted lines? You have to solve a triangle at a time. So my point is I'm going to start at A, then I go E and B. Those will be my next choices, B and E. But I have to decide whether I should go to joint E or joint B. If I jump to joint E, I will have only 2 unknown forces because I already calculated these 2 forces. Only these 2 will be unknown. If I jump to joint B, there will be 3 unknown bars. So it's better for me to jump to joint E. This is the strategy. Okay, so this is how we work. So off we go. I'm going to jump to joint E first because I'll get two forces. There's my 10K external force. There's my FAE. Notice I left the arrow. Whatever value I got for FAE, I copied. Remember, flip the arrow, not the value. So I wrote it as FAE as minus 14.4K pointing outwards. FBE downwards, FEF this way, 10K, this is external load of 10K. Okay. As usual, that angle is 45 degrees. So FEF is at 0 degrees. How about FBE? Can you see if I go counterclockwise from the x-axis, it's 270 degrees. FAE, I wrote down the value 14.94 negative, and it's making 225 degrees this way, counterclockwise from the positive x-axis. The 10K load is not this one. You got to go to the base, draw the line, and calculate that angle. Can you see that? Go to the base, draw the horizontal line, and then go that way. Very good. Here are your x and y components. From that you can calculate. This is pretty easy, right? So I just write down x cos, sin. So if you do that, it's very easy. You don't have to think about whether something's a cosine angle or sine angle. You just, as long as you measure counterclockwise from the positive x direction, the x component will only have cosines, the y component will only have sines. That's as easy as it gets. Now we're going to do for joint B. Here you go. There are all the external forces. This, we already calculated all of this. These two are unknown. We mark the angles. This is our force table. Counterclockwise from the positive x-axis, FBC is 10 degrees to the base. So we calculate to the base 0, 45, 90, 180. 0, 45, 90, 180. There they are. And then the x components will be cos. The y component will be sin times whatever this is. That's all. There you go. See, x component is all cosines, y component is all sines, and we solve these two equations for two unknowns. We will get them. Okay. Now you can go either to joint C or joint F or joint D. You can pick whichever one you like. As long as you have only two equations for two unknowns, you will be fine. Joint D is very similar to joint A, except it's flipped. Okay, it's all the other side, right? You can do the same thing. I'm going through this fast because by now you should see the trick. So again, I draw the angle FDC 180 degrees. FDC is 180 degrees. FDF is 135. This 10K is at 90. It's not this line. Go to the base, draw the horizontal, measure that angle. Then you can find the internal forces for equilibrium, x component, y component. You're done, no problem. And then off we go. And you can go to joint C. Joint C is an easy one. There are the three forces in joint C. You can draw them all, and you can find the angles. And as usual, you can find the forces. There's nothing to it. Okay. So now we are at the final result. These three, all of these bars are in tension. Sorry, this bar must be in compressions. That's not tension, that's C. Okay, that's how it works. I hope you got an idea of how the internal forces in a truss works. It's pretty easy. Summary, what you have to do is first calculate the joint forces by drawing the free body diagram of the whole body, and then go from joint to joint to joint to joint to joint, solving one triangle at a time. Thank you very much. I will see you later.